Okay, Assalamualaikum warahmatullahi wabarakatuh. Good day everyone. I hope you guys in a good condition. Stay safe, stay healthy and stay at home. Okay, I'm Ayumi and my other two teammates are Aisha and Akila. So now I represent to make a video of our group project. Okay, so our group choose question number 15, which is basically how to find the external reaction or reaction coordinate. So here the chemical reaction, which is 4HCl plus O2 produced to H2O plus 2Cl2. The data given is temperature 500 degrees Celsius and 2 bar for the pressure. So the question give initial mole, which is 5 mole HCl and 1 mole oxygen. What is the composition of the system at equilibrium? That means the question want the mole fraction in terms of reaction coordinate. Okay, here the table that we create to avoid to make a mistake. Okay, in this table, we put the delta H and delta G at standard state, which is 298 Kelvin, and value of A, B, C, and D. Also the initial mole, Stoichiometric coefficient, and also the final mole for each species. Okay. So the delta H and delta G we got it from table C4, while the value of A, B, C, D we got it from table C1. Okay, so next, this is the initial mole, which is from the question. Yes, so here this is the 5 mole HCl and 1 mole oxygen for the initial mole. Okay, so the H2O and Cl2 is 0 because there is no stated in the question. Okay, so Stoichiometric coefficient is from the Stoichiometric number in the chemical reaction. 4 HCl, 1 O2, 2 H2O, and 2 Cl2. And bear in mind that the product must be positive and the reactant must be negative, like this. -4, -1, 2, and 2. Okay, so the final mole is like this, which is this is the initial mole plus the Stoichiometric coefficient for the each species multiply with the extent of reaction. Okay, for example, HCl, 5 here is the initial mole and -4 is Stoichiometric coefficient and multiply with the extent of reaction. Okay, same goes to the O2, H2O, and Cl2. Okay, so this is the equation that I just explained, which is this is for the individual species, and this is for the when it comes to submission for all species, which is the n here is the total mole at final state equal to total mole at initial state plus total Stoichiometric coefficient for all species multiply with the extent reaction. Okay, here the total mole. Here the total mole for all species, which is here I show you, which is this one, initial mole, total initial mole. So 5 plus 1 equal to 6 mole. Also same goes to Stoichiometric number, total Stoichiometric number, which is -4 plus -1 plus 2 and plus 2 equal to -1. Okay, in order to get mole fraction of specific species, which is yi equal to, this one is number of mole of specific species over total mole of all species. Okay. If in terms of reaction coordinate, yi equal to, okay, I will explain again, which is this one is the number of mole at initial state of specific species plus Stoichiometric coefficient for specific species multiply with the extent reaction. Okay, this one is for individual species over n naught here is what? N naught here is total number of mole at initial state, which is given by the equation, plus total Stoichiometric number for all species multiply with the extended reaction. Okay, so this one is for when it involves all species. Okay, so for example, 5 HCl equal to 5. 5 is because the initial mole of HCl is 5 minus 4. 4 is the stoichiometric coefficient for HCl minus here because the HCl is the reactant. Okay, divide by 6 here is the total mole and minus external reaction. Negative 1 here because the total stoichiometric number is negative 1. Same goes to O2, H2O, and Cl2. Alright, then we need to find the standard heat formation, which is enthalpy at 298 Kelvin at standard state, equal to submission of product minus submission of reactant. Since from the reaction, the product have 2 mole of H2O minus 4 mole of the HCl, which is the reactant. So we got the value is negative 114408 joule. Okay, we just need to substitute the value of standard heat formation here that we already stated in the table earlier. Okay, so now the standard free Gibbs energy formation, which is delta G at 298 Kelvin, same goes like the heat formation above, which is the submission of product minus submission of reactant, and the Gibbs energy formation for H2O and HCl are also already stated in table, and the value is negative 75948 joule. Okay, after that we need to find the value of total A, B, C, and D. Okay, for example, for the total A equal to submission of stoichiometric coefficient for each species multiplied with the value of A for each species. Okay, I will show you how to calculate it from the table. Alright, okay. So, okay, here the stoichiometric coefficient and here the value of A. So, how to calculate it? Just negative 4 multiplied with 3.156 plus negative 1 multiplied with 3.639 plus 2 multiplied with 3.470 plus 2 multiplied with 4.442. Same goes to B, which is negative 4 multiplied with 0.623 plus negative 1 multiplied with 0.506 and so on. That's also same for C and D. Alright, so this is the value of A, B, C, and D. And then why we need to calculate this value of A, B, C, and D? Because we want to find the change of enthalpy and change of entropy. Okay, now so we need to find the integral heat capacity, which is the change of entropy, and we use this formula. And as we already find the value of A, B, C, and D, we just substitute in this equation. And before that, we need to find the value of torque equal to T over T naught equal to 2.5931. After that, we substitute in this equation, and then the value is negative 0.0744 joule per mole K. Alright. Next, the mean heat capacity, which is the change of enthalpy. We use this formula, and the step is just same like change of entropy. Just substitute the value A, B, C, and D, value of torque, and the value of Tina here, and the value of change enthalpy is negative 357.749 joule per mole. Alright. Okay, this is the definition of a standard property change of reaction, which is delta G equal to delta H minus T multiplied with delta S. So this is these both are the standard heat of reaction that related to temperature. Okay, we obtain this equation when we combine these three equations. Alright. Okay, by substitution of all these relations, we got this equation, which is delta G, and we need to divide it by RT. And this equation will be obtained. Okay, actually, this one is the change of the enthalpy, while this is the change of the entropy. So we already calculate it and just substitute here. Okay, why we need to find the delta G over RT? Because we want to find the value of K. Okay, when we want to find the value of K, general equation is negative ln K equal to delta G over RT. Delta G over RT here, we substitute with this equation. Alright, to find the value of K. Okay, I show you step by step to calculate the value of K. Here, which is this is delta G minus delta H extended state. We have already calculated it before over RT at 298.15 equal to 15.515. Right, then delta H at standard state over RT at 773.15 equal to negative 17.798. Okay, next. Okay, as I said, this is the change of enthalpy. The change of enthalpy that we calculate before, the value is negative 357.749, and we multiply with the 1 over 773.15, and the value is negative 0.463. Alright. After that, we just substitute into the equation, into this equation, and the value of negative ln K is negative 1.716. But we need to exponent both sides because we want single K. So the value of K is 7.18. Okay. Why we want to find the value of K? Because we want, back to basic, that we want to calculate the fraction coordinate, right? So we need to find the value of K. So now we have the value of K. So yeah, now we can find the value of external reaction. Okay. The external reaction here, we use this formula, which is multiplication of yi, which is mole fraction, multiplied with the fugacity coefficient and power of Stoichiometry coefficient for each species equal to P over P naught, power of negative V, which is the total Stoichiometry coefficient, and multiply with value of K. Alright. Why we assume the fugacity coefficient is equal to 1? Because when pressure is sufficiently low or temperature sufficiently high, so the equilibrium mixture behave essentially as an ideal gas. So we assume that fugacity coefficient is equal to 1. Okay, so now we need to multiply all the mole fraction, which is YH2O, YCl2, YHCl, and YO2. And YHCl and O2 at the denominator because of HCl and O2 are the reactant, and the value of the Stoichiometry coefficient must be negative. So we put it in the denominator to make a proper fraction equal to P over P naught power of negative 1 multiplied with K. So this is the mole fraction in terms of external reaction equal to 2 over 1 bar multiplied with 7.18, the value of K that we already calculated before. And then this is the way how we calculate the external reaction. Okay, actually this is the mathematical calculation, and at the end we obtain the value of external reaction using symbol lab. Because the power is higher and we can use our calculator, then the value of external reaction is 0.7934. When we already obtained the value of external reaction, equation already easy to answer. It's easy for us to calculate the equilibrium composition of acid gases which is we just need to substitute the value of ester reaction here and here, and we got the mole fraction for each species. Okay, so the final answer of acid gas composition of system at equilibrium for HCl is 0.3508, and for mole fraction of O2 equal to 0.0397, and mole fraction of H2O equal to 0.3048, and the last one is mole fraction for Cl2 equal to 0.3048. Okay, so I think that's all from me. I hope you guys can understand what I explained for this question. So thank you so much.